already covered the spring already, so I'm planning to move on. The next one will be pulley and belt. Okay. Pulley and belt. So for pulley and belt are very useful for transmitting the power from one part of the shaft to some other shaft. The advantage is that you don't need to have too many gears, and you can have a long belt, and which is allowing you to transmit the this rotation, just like your bicycle, right? So there are some common shapes for the belt. One kind is like a flat one, like a rectangular. Some are round ones. Some are in a V shape. And some are in multiple V shapes. Okay? So, depends on what kind of belt you are using. You are going to prepare the pulley. So the wheel is called the pulley, 皮带. The pulley will have this groove that meets the shape of the belt. So one thing you need to be concerning about will be how long the belt should be. Okay, and when you design, you can. This is just like your bicycle, and imagine you are going to use a belt to drive the two wheels. One, if you use pulley and belt, one connected to the pedal, the other one connecting to the wheel on the back. So then paddling allows you to drive the wheel from the back. So usually or typically there could be having different diameters of the pulleys. Okay, you can even have multiple pulleys. So because the belt is elastic material, it's quite, the force between the pulley and the belt is actually quite interesting. For the entire textbook, this is actually where you are going to solve for differential equations. Okay, later on I will show you. When you learn engineering math, you learn how to solve for differential equations. Differential equations can be seen a lot in many other subjects, but not so much in solid mechanics. However, this is one time that you will see differential equations. So let's talk about that later on. Let's first discuss about the length. So by geometry, you first need to figure out the angle right here. So because of the difference of the pulleys, so the tangent point is not right at the 90 degree, it's tilted. So you need to compute the length from the tangent point on the left to the tangent point on the right by some geometrical information. So I think those are quite simple, but it takes some time truly computed. If you do not compute the length of the pulley precisely or appropriately, maybe the belt you choose is too long or too short. If it's too long, then it's not tight enough. If it's too short, then it's too tight. Probably you have a hard time to put it on top of the pulley. Okay, and there are different ways to apply the belt on the pulley. There's a crossed type of arrangement. Then you need to have a different way for the length calculation. For the cross type, you are going to use the tangent point at the bottom right here on the left, and the tangent point on the upper right corner. Okay. The rest are just math. Okay. So, as you can see, just like how the first figure shows, you can see if you have a driver on the left, for example, a motor or you're paddling, you're kind of tightening the belt at the bottom. And the belt on the top is a little bit looser. So the tension force on both sides are different. That's the interesting part about the belt. The tension force on both sides are actually different. That's why earlier when we have a homework, if you remember, when we had a homework, and sometimes I give you a problem like this, and I show you distributed forces, and I said, okay, they are belt forces. In that particular problem, basically I am trying to show you the flat kind of belt, which is providing this kind of distributed load. And also, I was telling you that I have tension forces on both sides, and they are different. The reason why the tensions on both sides are different is basically what this chapter is talking about. Because they are elastic material. When you drive the pulley, one side of the belt is tightened, the other side is a little bit loose. Okay? And that actually generates a torque because there's a force difference. This is a unique way to change the working plane of the pulley, where they twist the belt a little bit by a certain angle. In the textbook, we don't talk about this kind of application, but you do see the advantage of using pulley and belt. You don't really need to have pulleys in the same working plane because the belt are elastic materials. But for the later on discussion, we only have examples that are in the same working plane. Okay, and that's fine. I want to move on to this part. This is where you now have the differential equation. Okay, what's happened? So, if you take a look at the pulley, this is one pulley and this is one belt. Okay? center point, tangent point, okay? So if I focus on a small portion somewhere right at the right in the belt, and somewhere that is contact to the pulley, then if you exaggerate how the cut look like, it's gonna be like this. So let's take a look at the force diagram for that small cut. So if we say from some coordinate system, you have a theta angle up to a certain point. What does that mean? That means if you treat this position as theta as 0, then you are studying some small cut right at the angle of theta, and you made a small cut of d theta. Okay? Then let's assume you have certain tension force from the right side. So there's a tension force on the right side, F. And because the tension forces on both sides of the pulley will be different, then the tension force on the left side of this small element definitely will have some changes of the tension force. That's why it's assumed to be F plus certain increment, dF. So the increment could be negative. So basically, in this schematic, it's assuming on the left-hand side there's a change. So the change could be negative or positive, we don't know. So we use a dF to represent the change of the tension force. And if we assume this part is larger, then we will have, it's like you are dragging the pulley, dragging the belt on the surface of the pulley. So between the pulley and belt, there's some friction, and the friction is against the direction of your motion. That's why it's along the negative direction. So F represents the friction coefficient. And since your belt is mostly rotating in a pretty good speed, so there will be centrifugal force. So let's say there are some increment of the centrifugal force, ds right there. And also you have the pulley that is holding your belt, the normal force, supporting force. So the normal force between the belt and the pulley will be dm. Because this is a small cut, so all the forces are just a small increment. And since you have normal force right here, so at the very bottom of this belt, the total friction will be friction coefficient times the normal force. So that would be the force diagram that we are working on. And the centrifugal force can be computed by I omega squared. And let me see, this is the radius. So R d theta is the length. And M is should be mass per unit length, if I'm right. So M right here is the mass per unit length. So M R d theta would be the d mass. So the mass of this small cut. The mass times omega squared r. So double check. MR omega squared, yes. So this is basically D max, because you only have a small cut. So M is the mass per unit length, and the arc length will be R d theta. So M R d theta is dm. The radius remain constant. Omega remains the constant. So only the mass matters by the size of your cut. So that's why it's a mass is a dm. So the centrifugal force equals to mr omega squared, and then after derivation at the end, you can get because v equals to omega r, so mv squared d theta. Just assume it as a centrifugal force, so mv squared. But right here, n is the mass per unit length. V basically is the speed, meter per second. Now, they use force of balance of force. So what's happening is they are studying this in the tangent direction. Okay, along this, I should say tangent direction, transverse direction. So F is actually following this arc, so it's not lying on the perpendicular line right there, the tangent line is not. So there should be a angular correction. So in fact, if I exaggerate it, if this is the tangent line, then this is the direction of F. So there's a angular difference of half of the theta. Because you correct half of theta here and correct half of theta over there. You share the half over the theta. And here, half over the theta. Okay? So, because the d theta is so small, and here when you are trying to compute cosine half over d theta, it's almost the same as directly computing half over d theta. So right here, it's actually computing along the radial direction, sorry. So they are trying to study along the radial direction. So over here, there's a centrifugal force going outward. So ds, there's a normal force, dn, and also there would be forces going down here and forces going down here. So they would be F times, this is sine half of the d theta. So sine half of d theta is almost the same as half of d theta because the d theta is so small. Okay, that's why you have positive ds, positive dn, and going down, negative f times half of d theta, and going down, f plus df times half of d theta. At the end, you end up with this equality, balance of the forces along the radial direction. To reorganize, you at the end up with this relationship. If you have this small angular increment, then something increases at the same time. First, you have an increment of the normal force, but it equals to your force times your increment of your theta minus the increment of the centrifugal force. This is the balance between normal force, centrifugal force, and also the tension force. Okay? So how come dF disappeared? Because right here, dF times d theta will be way smaller than all the d terms. So this is much smaller than other d terms, so dF disappeared. So what's interesting is that dF disappeared. Okay, what's next? You can then, this is the other part. This is for the transverse direction. For the transverse direction, is right here. You are going to use f cosine half of the d theta. And because the d theta is so small, this is almost the same as f. Cosine equals to 0, equals to 1. So that's why if you treat this direction as positive, then you have positive f plus df, but there is actually a cosine half of the d theta, but almost the same as 1. Here you have minus f, and you have friction. Okay, so this gives you equation between the increment of the df of the f. So df is shown in the balance of the transverse forces. So df now equals to f dn. Okay, and from the last equation, we already know what is dn. dn equals to f d theta minus ds. So you can plug it. So they plug it in. So dn is replaced by f. This is the friction coefficient. This is tension force, d theta minus friction coefficient, centrifugal force. And centrifugal force was derived earlier. ds was fc d theta. So you can just plug in. And also fc was derived. So after you plug in centrifugal force, you have friction coefficient, mass per length, radius, omega, and then d theta. At the end, you end up with an interesting equation where you have your tension force, increment of theta, and many other constants. You assume the friction coefficient is the same, mass per length should be the same, radius of the pulley will be the same, omega same speed. So the rest are just constant. Only thing that changes will be F, because F, as I mentioned at the very beginning, the friction, the tension force here and the tension force here are different. So the tension forces F varies everywhere. Right now what we are trying to compute is how f changes with theta. And this is how. At the end, you have a force equation in terms of theta. So this is a differential equation. First order derivative of f with respect to theta minus a constant term multiplying the variable equals to some constant, right? So this is a differential equation. So if you solve for it, you realize you can use an exponential model. Okay, so you just have unknown parameters a to be determined, and if you use the boundary condition, f at theta equals to 0 equals to if you call here boundary condition, if you call this f2, okay, and that means right here is f1. So if you say when theta equals to 0, f equals to f2, then by this boundary condition you solve a equals to f2 minus some constant. Okay? And use it, you end up with the general equation right here. Okay, so f is a exponential function. When theta equals to 0, then this term and this term disappear, and at the end you have f2. But you also need to know the relationship of f1 and the total angle. If you call this total angle phi, okay? So when the force equals to right, when theta equals to phi, you claim your force equals to F1. So this is where you make both equals to each other. F1 equals to the general equation, but your theta now is phi. Okay, so applying the boundary condition on the other end. So at the end, you have this equation, and you can try to play with it to figure out, to come up with some relationship between F1, F2, F centrifugal force, and also the angle, phi. Okay? So now you can actually compute the tension forces everywhere, because all you need to do is to apply certain angle. So when theta is 0, you have set the tension force F2 right here, and if you investigate anywhere along this arc at any theta, you just need to plug in the angle theta into the equation. You will get what will be the tension force anywhere. And if you reach to the other tension point, the angle at this condition will be phi. Then you will have the F1. Okay. So the rest are just trying to describe the same results in a different way, different format. What would be interesting is when they make a drawing to see where. This PowerPoint doesn't have a drawing. Okay, let me show you somewhere. Let me see. Right here. Maybe not exactly what was talked about in the slide, but I just want to show you. This is the exact same analysis. Okay, and I just want to show you that particular figure, the exponential function. Here. So these curves are the exponential functions. So for the entire belt, the tension inside the entire belt varies every minute. Okay? So if in this case F1 is larger than F2, and if you take a walk, for example, here is theta equals to 0, here is theta equals to phi, and here is the tension force. So initially, when you are somewhere inside the belt, then the belt force is the same. Okay? So this is F2. And after you walk to the other edge of the tension point, the tension force becomes F1. So it's like this. Here is F1. So what's in between is an exponential function. So it's gonna look like something like this. Okay? Just like these. Exponentially increasing. And sometimes you need to apply a tension force in advance. So there are even research about having a pre-stress. So this one doesn't show the pre-stress. Let me see if I can find. Doesn't show. Actually, yes, it has a diagram. Okay, so if you apply a pre-stress, this part is like the pre-stress. Okay, and this is the F2, this is F1, okay? So in this particular case, because you are driving counterclockwise on the left of the pulleys, so you are making F1 tighter than F2. So the tension force F1 is larger than F2. So you will have this scenario. If you take a walk from point A and then walk counterclockwise, and then walk back to A, you will see a greater tension force of F1. And when you reaches point B, the tension force starts to drop exponentially to F2 when you are reaching point C. And the tension between C and E remains the same as F2. And starting from point E to point F, the tension force starts to exponentially increase like this, and then stay as F1, just like what I have shown you right there. Okay? So the force difference would be delta F, and when you are trying to compute the power, required power to drive the belt, you can use the force difference multiplying the radius. Then that's torque, right? So when you are designing a pulley and a belt system, first you need to figure out what's the required length for the belt. Okay, making sure you can assemble everything properly. Then you need to figure out how much power you need to generate in order to drive the pulley in a certain way so that you will see certain force difference on both sides of the pulley that generate torque because of the torque that drives your shaft. And of course, that torque drives your shaft and also twists your shaft. So when you drive the pulley when you drive the shaft system by the belt, the advantage of this elastic belt is that it's gonna generate unbalanced forces on both sides, so that you will have a force difference on both sides. The force difference allows you to have a torque, but that of course applies some force to your ship. Okay. So let's see. Right here you can see some of the models. They look like this. That means they are built based on statistical model. Okay? So from each manufacturer, it will provide you certain information about the stress and number of basically cycles. Okay, so you will basically you can compute the life. Okay, but whenever you see a model like this, you see a constant right here and some power with a unique, a very weird number. Basically, they have done tons of experiments, and then they have a fitting model at the end. Okay. So let me see. So there's a process of making selections. Okay. So right here is showing you some steps. So if you need to find this exponential value, exponential of f phi. So phi basically is from geometry. So depends on what's your the size of your pulley and also distance between two pulleys. Then it determines the tangent points. F is the friction coefficient. So it really depends on what kind of material you're using. So you should have a constant friction coefficient. Using that, and here is this is the model that was shown. This is a metal belt. By the cycles, then is telling you the strength of the model. And also, here are some other models I didn't talk about. So basically, it's trying to some other models to compute the tension force on one side. And if you are able to compute the tension force on one side, then the tension force on the other side can be determined. And delta F depends on the power you generate. So torque is the power you generate. So with that, you can do further integration. Okay? But I didn't talk too much about the metal one because I think the procedure of designing belts are the same, but the metal one has more models. So for the elastic belt, let's take a look at one example. Okay, so this is more like a polymer type of belt. So right here is a flat belt, okay, and it's telling you that there are horizontal shafts with a center to center distance 4.8 meter, and the velocity ratio is given. Angular velocity of the driving pulley, the smaller one, is driving the larger one. Speed is 860 RPM. And then there's a driving power, 44,000 watts. And from here, it's already providing some extra parameters that's required. It's telling you the diameters. Let's see. Because of the velocity ratio, so the small one is in the diameter of 400, the large one is 900. Okay, and then let's see what else. The center to center distance 4.8. Okay. So I didn't cover everything, so I will just talk about the things I covered. Let's say you figure out the friction coefficient 0.8, and this is basically the power. I didn't talk about the like a correction for the, it's like a effectiveness of the power. So this is like the required torque is 44760, but your motor needs to have this amount of power in order to drive it, because due to energy loss and some other issues. So let's say you just have a motor that can generate 44760 watts of power. Then the torque can be computed by power over the speed. Okay, so at the end, the torque was computed. So once you have the torque, what's next is to, again, just like how they suggested for the metal belt, you figure out some geometrical information. So right here basically is the geometrical information that was done at the very beginning. where you are trying to figure out phi right here, right? Equation is right here. So they just need to figure out, okay, what's the angle, okay, between two tangent points. Okay, once you have it, with the known friction coefficient, you can have this value exponential f beta. Later on in the general equation of f1 and f2, you will need this value. Right here are some, this is to compute the centrifugal force. This is compute the velocity. This is basically computing the weight per length, right? So, but it's a weight force per length. That's for the calculation of centrifugal force. Once you have those, from the equation that we had earlier, you can, then this is delta F. From the power, from the torque you generate, you can compute the delta F. And then at the end, we can have a general equation basically between the F1, F2 centrifugal force and the small f phi. Okay, so here it's designing for the belt width. So there is for the problem, there is an unknown. He's trying to design the belt width. So the centrifugal force right here, the problem has an unknown. Okay, so for the geometrical information, when it's computing the weight force per length, there is a geometrical unknown parameter b. That's why later on when you plug into all the equations, there's a unknown b to be determined. With the equation that was derived earlier from the differential equation, you then have this equality. So all you need to do next is to solve for b. So at the end, it was found, okay, b has to be 210 millimeters. Okay, so then you can design the size of your belt. Okay, so I think for today's message, I just want you to know the force analysis in belt and pulley. So please remember, for belt and pulley, there is this kind of relationship where the tension force on both sides are different. And if you want to really know how the tension force increases with the increment of angle, you need to solve for differential equation. At the end, you are solving this differential equation, and you will build a relationship of the tension force on the larger side, tension force on the smaller side, and which is having this equality that is related to the mass per length, radius of the pulley, your omega speed, friction coefficient, the angle of the pulley. So please remember, they are related in this way. So in the future, when you are really designing for a pulley,
design this from scratch. You derive the equations from scratch. It's gonna, it's not easy. So I remember there are some extra information that you can know. Let's see if the slides has it. Okay, so I think in practice, sometimes you will need to change the tension. So this is one way for you to tighten the belt. So you can have certain mass right here with an extra wheel, so you can tighten it if your belt is not tight enough. And also the schematic B is to let you know if you have a system with a pulley and a belt, and the system may be connected to some other geometry, then there's a force balance, right? So you may be solving for certain force balance, okay? And also be aware your belt has certain weight, so it actually drops. So there's, in reality, the belt is not, if it's placed horizontally like this, is not ideally like a straight line. It drops a little bit, okay? So there are some, it's called a dip. It dips lower. So there are certain ways to compute the dip. So anyway, there are small details mentioned in the textbook. I'm not going to cover all of them. And let me see. For the V belt, it's more complex because the geometry, as you can see, is in a unique V shape. So usually you need to design your pulley based on the category, because you can only buy the V belt in certain shapes. So that's why right here the manufacturer will give you certain numbers with for the geometry. So you probably won't be able to randomly choose your parameter, your geometrical information. Okay, and when you are calculating for the length, it's remember it's slightly different, but I think it's slightly corrected by there's a equation to due to the weird unique shape of the V belt. So the length of the belt has to be calculated in a certain way, and the center to center distance has to be computed by this equation. But, I'm not going to prove why. Okay. So now you know, if you are using flat belt, the geometrical information is easier. You can just treat it like a thin wire, and geometrically you can easily compute the length of the belt and also center to center distance. But for V belt, there are certain equations to follow. And let's see. So over here, the power needs to be adjusted. When you apply certain power, you need to, there will be correction factor. So basically, your 100% power won't be 100% transmitted into the shaft system. There will be some energy loss. So for V-belt, there are factors to correct. This is more, they are geometrical informations, and also depends on the angle of your rep, and also depends on the length of the belt. So the book provides, all the tables from the book was provided by the manufacturer. So they give you a table. It tells you, okay, if you have one V belt or double V belt, how the K1 coefficient should be computed. Okay, and this is the correction for the belt length. In different length of the belt, they have different correction factors. So basically, the power changes with different geometrical informations. And over here, this is an equation that we have seen earlier, but here it's already telling you the F is 0.5123. So this manufacturer already tells you the friction coefficient. Okay, and so from the nominal power you computed earlier, when you apply to the real application, there is again another round of the correction. So these two parameters, basically, I didn't mention earlier, is like this is more like in different levels of your service, and also this is how much you want to design. If you only prepare certain amount of power, sometimes it's not enough. You need a factor certain times larger than the requirement. So it's like it's not for safety. It's a factor that allows you to drive the shaft. Okay, so over here, this is the correction factors in different levels of the surface. So if you have heavy shock, then your power needs to be strong. Okay, so for the V belt, it's quite interesting. The belt forces will be slightly different from what you have seen earlier in the flat belt. So the tension force there is a large increment. There is some increment on the belt force when the V belt contacts with the pulley. Okay, this is the uniqueness of the V-shaped belt. Okay, so it's not a original belt force. There's an increment, and the increment, I remember, can be computed with FB1. Table 17 points. This one. KB and KC. KB and KC. This is centrifugal force. This is the tension force F1 and F2 when there's no contact connection with the pulley. And when there's contact, there's an increment of FB1, and there's a different FB2, right? So we just need to figure out where is FB1 and FB2. Here. So the tension forces needs to be will be increased by FB1 and FB2. But how do you compute it? FB1 equals to KB over small d, FB2 equals to KB over capital D. So what is KB? KB is given in the table of 17-16. So right here, in different belt selections, different categories, the values of the KB varies. So you can actually generate stronger tension forces when your V belt connects with the pulley. So if you are requiring stronger tension forces, then you have stronger friction between the pulley and the belt. V belt provides this opportunity because it has more contact surfaces. So how much additional tension forces can I generate? Depends on what kind of shape you are choosing. So from the manufacturer, it tells you if you choose different selections of the V belt, you will have the corresponding KB parameters. So those KB parameters divided by its pulley radius would be the additional tension force you generated between the V belt and the pulley itself. Okay, so that doesn't change the delta F between F1 and F2. It just provides a stronger grip between the pulley and the belt. Okay, so maybe if you are using it for some kind of machine that doesn't allow slippage between the belt and the pulley, you need a strong connection between the pulley and belt. Then V shape probably is the selection. Okay. So I think I pretty much covers what I want to talk about. I'm not going to talk about timing belt and roller chain, but just for you to know, in the future, if you check on the textbook on this particular chapter, there are two more kinds of deformable components. One is the timing belt, the other one is the roller chain. So for the roller chain, what you will be analyzing is how strong is the element inside the chain. Okay. So there are, and also the sprocket. So there are actually, for the roller chain, you are having this gear-like geometry, but it's called a sprocket. Okay. Gears works with gears. Sprocket works with the roller chain. Okay. But they are looking like a wheel with teeth. Okay. So I will not cover everything. Just for you to know, the manufacturer actually provides tables in in the past, I remember in this particular portion, it's a lot of table checking. Okay, at different speed, different number of chains. Okay, what would be the power? And there are different categories. This pink line represents the separation of type A, type B, and type C. Okay, this is how you read the table. This manufacturer has different types of chains. Type A follow this part, type B follow this part. As you can see, type A is for lower speed, type B slightly utilized for a little bit greater speed, and a little bit more faster, type C, and there's a extension of the table, something like this. So why don't they provide certain analysis for the chain and the sprocket? Because it's complex. You know, the geometry of this is complex. So whenever you check the textbook and you realize they didn't provide too much derivations, usually it's because the design is complex. So what they can do is to do a bunch of experiments. They either provide you a regression model or they put the experimental data in a table. Okay? So for your reference, in the future when you design for roller chains, it's you have tables. Okay, so I think that's pretty much. I don't want to cover the wire ropes. Forget about the wire ropes. Okay, just quickly talk about the key information of wire ropes. Wire ropes are so commonly used for bridges, elevators, and cranes that carries a strong payload. So basically, they are unique ways to wrap those metal wires. They may have wires in different diameters. In order to see how they wrap them, is to cut them in half, then you will see the cross section. So what's interesting about the wire rope is that if one tiny wire breaks, the whole thing doesn't break, right? So it's kind of like a redundant design. You have multiple levels of safety. As long as not all the wires breaks, then the rope is still there. But of course, for maintenance, when they see some small wires breaks, they know, okay, it's time for replacement. So for mechanical design of wire ropes, you basically try to figure out the stress analysis inside the wire rope. So there will be tables again, and it's gonna tell you one important information, which is the effective area. Let's see, where is it? Effective stress area. Okay, I think I couldn't find it, but this part is interesting. Probably important for you guys to kind of understand the safety factor for wire ropes. So what's the safety factor for our elevators? Depends on the velocity. It could be as large as 10 times larger than the forces applied to the wires. Okay, that's how safe our elevator is. But if you does that mean if the elevator says you can carry one person, you can actually stand 10% right? Maybe. But the 11th one stays up there, then it will break. So probably is how that means. Okay, anyway, so it kind of, I just want to let you know, elevator probably is because you are carrying human life. That's why the safety factor applied to wire ropes usually has a recommended level of safety. And for elevator, it could be as large as 10. Okay, anyway, the textbook includes wire ropes. What else? I think that's the end. Okay. Yeah, that's the end. So in today's introduction, I spent most of the time on pulley and belt because I think that would be the for your own exercise or future research or future work, probably pulley and belt would be the most common component that you will be designing for. And of course, you could be designing for chains and sprockets. You could, but for the chain and sprocket, as you can see, there's not much calculation to be done. It's mostly checking the table, so you can easily just follow the table. And even for the timing belt, there's also not much about the part. So designing for the pulley and belt requires more knowledge about the differential equation right at the contact between the pulley and belt. So I think if you need to spend some time on the design of deformable components, probably you will be studying for pulley and belt. Okay. So that's what I want to cover today, and we are right here, right? So next week, we are here. So tomorrow I probably can talk a little bit about clutch and brake. I try to cover those components. I just want to cover the ground. I don't want to jump into certain derivations and ask you to solve problems, because I want you to know more about those mechanical components. So there are still welding parts and clutches to be introduced after tomorrow. Then next week, I will be serving as a judge in Taichung. So Dr. Patel will be here. He will listen to your progress report. So last time when you proposed, there there's already some comments to each of your team. So please continue to work on the project and present your progress to Dr. Patel. He will help you to make adjustments. And then for the rest of the weeks, if I'm done with all the components, then we can have more time on project discussions. Okay, and maybe we can have extra weeks for project for deeper discussions. Okay, so that's it for today. Before you go, please make sure you check attendance. Any questions?